All right, let's start talking about how our relations can be transformed. So 4.3 is called the transformations involving A. Now, we already talked about the standard form of a quadratic. Now, if you remember, the standard form for a quadratic relation is y is equal to ax squared plus bx plus c. This is our standard form. Now, the simplest form for any quadratic is simply y is equal to x squared. That means b is 0 and c is 0 and a is a 1. So it's just y is equal to x squared. This is called the parent relation. And the reason why it's called the parent relation is because all other forms of quadratic relations can be derived from this. So this is the most basic form possible. We're going to show you what this looks like in just 1 second. Now, we can rewrite this equation in the following form. Y is equal to a times x minus h bracket squared plus k. This is what we call vertex form. And the reason why it's called vertex form is because we can figure out what its value is, what all the variables are from the vertex, but we can also look at it and determine the vertex from the equation itself. That's generally speaking the idea. We can graph parabolas in this form simply by performing operations called transformations. And there's a certain set of transformations we're going to talk about over the next few lessons, but we're going to keep it simple to start with. All right, so on the left-hand side here, it says, the question says, complete the table of values and graph each parabola shown below on the same grid. And the reason why we're putting it on the same grid is so we can see the difference between them. All right, so on the left-hand side, we see the parent relation. And for each of these, we're going to do the parent relation every single time so we can see how it evolves. So y is equal to x squared. So negative 2 squared is going to give us 4. Negative 1 squared is going to give us 1. 0 squared is 0, 1 squared is 1, and 2 squared is 4. 4, 1, 0, 1, 4. Every single time from these following x values. Now what we're going to do is we're going to take our new equation, which is y is equal to 2x squared, and we're going to see how that changes things just a little bit here. So we're going to take those same values of x and we're going to substitute it into our new equation. So x squared, which is 4, times 2 is going to give us 8. All right. Negative 1 squared is 1 times 2 is going to give us 2. And 0 squared is 0 times 2 is still 0. 1 squared times 2 is going to give us 2. And 2 squared, times 2 is going to give you 8. All right. Well, let's take a look at that graph and see what it looks like. Let's graph the parent equation first. So we have negative 2, 4. Negative 2, 4, all the way up here. All right. And then we have negative 1, 1, 0, 0, 1, 1, and 2, 4. This is what the parent equation is always going to look like. All right. Let's switch colors for a second. And now let's do our new equation. So we have negative 2, 8, all the way up here this time. And then we have negative 1, 2. 0, 0. And then we have 1, 2. And 2, 8. Now let's graph this one. All right, so just like always, we have to label our curve or label our entire graph. So this, our second one is y is equal to 2x squared. And our first one is y is equal to x squared, the parent relation. So looking at this and trying to figure out what the difference is, even though they both have the same x components, how do the y's change? That's what we're really kind of digging into here. So in the table below, what we're going to do is we're going to compare the new parabola, y is equal to 2x squared, to the original parent function, y is equal to x squared. So let's take a look. So on y is equal to x squared, where is the vertex? Well, the vertex is at 0, 0. We can see that's where it changes directions. Direction of opening, well, it opens up. All right. Equation of the axis of symmetry. So this is straight down the middle where it hits. It's always going to be the x component of our vertex, so x is equal to 0. Now let's look at y is equal to 2x squared. Where's the coordinates of the vertex? Still 0, 0. And it still opens up. And its equation of the axis of symmetry, it's still 0. So none of that has changed. It's basically the same equation, but something has obviously changed. We can see this. So what has changed? Well, we can see that if you look at every single y component, it's kind of been stretched, like you're pulling it, like you're pulling an elastic. You've stretched it vertically by a factor of 2. So every y component was stretched vertically by a factor of 2. So we could say, describe the transformation made by the graph of y is equal to x squared. Made from the graph y is equal to x squared, we can see that it is a vertical stretch by a factor of 2. Now, instead of writing by a factor of, because we're going to write it so often, typically we write just BAFO, by a factor of 2. All right, just it's a lot easier because we're going to be doing it so often. Okay. So this is a vertical stretch by a factor of 2. Where does the 2 come from? Right there. So we took the original parent equation and we multiplied it by 2. So that is where that 2 is coming from. All right, let's investigate this just a little further. By that, I mean quite a bit further, of course. Let's go do it again. Now we're going to see how the equation or how the graph keeps evolving based on how we change that value in front of the variable, the coefficient. All right. Too much clicking. 1, please. Right there. Complete the table of values and graph each parabola shown on the same grid. Again, we have the parent equation. We know this one was 4, 1, 0, 1, and 4. Now here's our new equation. Y is equal to negative x squared. Remember, the negative is applied afterwards. If I just look at that original one, that's going to be negative 4, negative 1, 0, negative 1, and negative 4. So let's graph it just to see what it looks like. So we have negative 2, 4. We start up here. Then we have negative 1, 1, 0, 0, 1, 1, and 2, 4. All right, this is our y, this is our x, and this is y is equal to x squared. All right, let's switch to our red pen now. So this one, we have negative 2, negative 4. Negative 1, negative 1. 0, 0, 1, negative 1, and 2, negative 4. They look almost identical, but they're not quite. It's almost like if the x-axis was a mirror, we can see that the red parabola is almost like a perfect reflection in the x-axis of the original parent equation. Oh, interesting. So let's take a look at this a little bit further. Remember that we have that original equation, y is equal to a times x minus h squared plus k. What we're looking at here is that value in front of the x, if we look at this equation, is the value of a. So in this case, a is equal to 2. Down here in this one, a is equal to a negative 1. Okay, so let's compare these things. Our coordinates of our vertex for the parent equation are still 0, 0. Nothing's changed there. It's still opening up. In the axis of symmetry is x is equal to 0. Nothing's changed there. Now for the next one, yeah, it still has a vertex of 0, 0, but now it's opening down. And the reason why it's opening down is because a is less than 0. We saw this in a previous lesson. The equation of the axis of symmetry, that hasn't changed. It's still at x is equal to 0. So what can we write as changed? We can say, as I mentioned before, it kind of looks like a mirror here. We can say that the transformation made from the graph of y is equal to x squared has been a reflection in the x-axis. A reflection in the x-axis. It's like it get flipped over top of the x-axis. Oops. Okay. Now going below, it's basically just more of the same, except the equation's getting a little bit more challenging here. Here we can see that the value of a is -3. Okay. Now let's see how this changes things. So we still have our parent equation, which has a y of 4, 1, 0, 1, 4, because we're still doing it across the same x components. So if we substitute those values in, -2 squared, that's 4. 4 times -3, that's -12. -1 squared is 1. 1 times -3 is -3. 0 squared is 0 times -3 is going to give us 0. 1 squared is 1 times -3 is going to give us -3. And again, -12 down here. So let's graph it again. So we have -2, 4. -1, 1. 0, 0. 1, 1, and 2, 4. So there's our first equation, our parent equation. Y is equal to x squared. Okay, we have our x and our y axis. Let's go to the next one, our red. So -2 all the way down to -12. Okay, -1 down to -3. 0, 0 is still there. And then 1, -3. And 2 all the way down to -12 again. So if we draw this, this question is basically a combination of the first few examples that we did. Just write this out. Y is equal to -3x squared. A combination of the first couple we did. We can see that it has been stretched. We can also see that it's been reflected. Good to know. All right, so let's write out our data. First of all, y is equal to x squared. Comparing the coordinates, yes, the vertex is still 0, 0. The direction of opening is still up for the parent. The equation of the axis symmetry is still x is equal to 0. How about the new parabola, y is equal to -3x squared? Coordinates of the vertex, yep, still 0, 0. And the direction of opening, oh, it's going down this time. Again, this is because a is less than 0. A is -3. Okay, you don't have to write this a is less than 0 every time. This is just me trying to exhibit y. And the x-axis hasn't changed. It hasn't moved in any way, shape, or form. So that's still x is equal to 0. So let's write what has changed. Well, first of all, it's been stretched again. So we can say that, pardon me, it's been stretched vertically, but it's also been reflected. So we could say reflected in the x-axis and vertically stretched by a factor of 3. We're just going to write BAFO. By a factor of 3. Huh. Okay. So is that everything that we're going to learn here? Not quite. We're going to do one more example, and then we're going to kind of summarize everything for you. So here's our last one. The equations are slightly more complicated. So again, we're going to start with the parent equation. And we're starting with the exact same x and x components. So we're still going to have 4, 1, 0, 1, 4. So we can graph that in. So we have -2 all the way up at 4. -1, 1, 0, 0, 1, 1, and 2, 4. All right, drawing it in. We have our x, we have our y. Y is equal to x squared. Okay. Now, from here, we have y is equal to 1/2 x squared. So in this case, our a is equal to 1/2. All right. So let's do our substitution. -2 x squared, or sorry, -2 squared, that's 4. 4 over 2 is 2. All right, let's go to the next one. So now we have -1. -1 squared is 1. 1 times 1/2 is still 1/2. or you can write it as 0.5, however you'd like. 0 squared is 0. 0 times a half is still 0. 1 squared is 1. 1 times a half is 1/2, or 0.5. And then finally, 2 squared is 4. 4 times a half is just a 2. All right, so let's graph this new one. Let's use red here. So we have negative 2, 2. So right there. Negative 2, 2. We have negative 1.5. So negative 1 right there. And then still 0, 0. 1 and 1/2. Okay. And 2 and 2. So if we're to graph it this time, we have y is equal to 1/2 x squared. Did that give us everything we need? Well, let's check out all of our data. First of all, coordinates of vertex for y is equal to x squared hasn't changed. Still 0, 0. It still opens up. And the equation with axial symmetry is still x is equal to 0. How about the other one? In this one, coordinates of the vertex, yep, still 0, 0. That hasn't changed. Pardon me. This one is opening up. And its equation of the axis of symmetry is still x equal to 0. So it still has all of those same basic properties. So how does it differ? Well, it's not reflected. And it's not stretched because it doesn't look like I've pulled all of the y values. In this case, it looks like I've pushed all the y values down. For that, we use the term compression or compressed. So we can say that this parabola has received a vertical compression. Like we're squishing it down. Vertical compression. Vertical compression, or you could say vertically compressed. By a factor of 1/2. Okay, so let's summarize everything we learned today. Okay? So first up, if the a value is, we're going to start every sentence with that. If the a value is. If the a value is what? If the a value is a positive number, so if a value is strictly greater than 0, not equal to 0, strictly greater than 0, what does that mean for the parabola? It means that it opens up. Okay? It opens up. If it is a negative value, so if it's less than 0, which we saw that too, quite a bit, that means it opens down, and we have a curve more like that. So this means that if we have a negative, if we have a negative a value, the parabola opens down. This means that there is a reflection on the x-axis. Now you've probably seen this term before, the term absolute value. So if I have the absolute value of, let's say 7, then the result of that is just 7. If I have the absolute value of negative 7, it is still just 7, okay? It always gives us the positive value. These signs, absolute value means the magnitude, the scale of our value. If I do something like this, the absolute value of, let's say, 2 minus 4, then it's going to do the 2 minus 4, which is going to give me negative 2, but then the absolute value of negative 2 is just simply 2, okay? So that's what absolute value is. So the absolute value of A, the magnitude of A, is always the positive outcome regardless. So the absolute value of negative 3 is just going to give you 3, just to give you an example. So how does that help us? Well, if you have an A, remember, if the A value is greater than 1, if the A value is greater than 1, what that means is that the curve is actually being vertically stretched by a factor of magnitude of A, all right, or absolute value of A. So vertically stretched, it's being pulled. All right, it's like you're grabbing every y value and pulling it up. Similarly speaking, if you have an a value that is less than 1 but greater than 0, okay? If you have an a value that's between 0 and 1, so maybe it's 0.5, maybe it's 0.3, okay? If you have an a value that is between 0 and 1, that means that the parabola is going to be vertically compressed. Remember, we're talking about the magnitude of a here, right? the absolute value. That's why we don't have to check negative values. Okay, so if it's greater than 1, that means it's being stretched. If it's between 0 and 1, that means it's being compressed by that factor of absolute value of a. If a is exactly 1, that means that you're basically multiplying every y value by 1, so none of them are changing. So there is no vertical stretch or compression. So that's really all we learned today. We learned about the vertex form, which is y is equal to a times x minus h squared plus k. We learned that. We also learned all the different properties of these various values. We learned about how a changes things. So in terms of whether it's greater than 0, less than 0, that tells us whether it stretches, compresses, it tells us whether it's a reflection, lots of information there. So that's it for this one. The next one, we're going to dig a bit deeper on that h and on those h and k values. Good luck.